Today we are counting functions and discussing the Pigeonhole Principle. Well, some things we know, so let's just start off and suppose we have two finite sets, A and B, and such that, let's see, the cardinality of A is n and the cardinality of B is m. And then let's think about some things that we can count. Okay, first of all, the number of relations from A to B. How can we count this? Well, let's think about what is a relation from A to B. By definition, a relation is any subset of the cross product. And this is the case if and only if R is an element of the power set of A cross B. And now we can really think about counting these things, because what do we know? We know the cardinality of A cross B is n times m. And so if you think about the power set, it's 2 to the n times m. So the answer here is 2 to the n times m. This is the number of relations. Okay, what else can we count? Well, let's count the number of functions from A to B. Now this we're going to have to do a little bit more thinking. We know, for example, every function is a relation, right? That's how we started functions day one. It's a relation from A to B such that, and then we had some properties, but maybe for this, let me give some specific elements. So A is going to be A1 through AN. And now how can I think about a function? Well, we can think about describing a function by first having a f of A1, and then f of A2, and then f of A3, and then we just keep assigning, and for each one of these we just pick an element of B. We have m possibilities here, and similarly for this value A2, what's going to be f of A2? Well, we have m possibilities here, and then we have m possibilities for f of A3, and then we keep assigning, and this is the last one. And you can really, well, let me write the answer and then I'll make my comment. The answer here, as we see, multiplication rule, it's m to the n. But what I was starting to say is in this one, if we had A here, B here, right? How do you assign? And this is something we talked about in our functions videos. Well, it's in this order. Here's A1. We have 3 choices, right? So maybe I pick this one. And then the next one, A2, I have another 3 choices. Well, maybe I also pick this one. Then here, we have 3 choices, right? And maybe here I pick this one. That's how this multiplication rule happens. And this is the number of all functions from A to B. Now, one more thing we will count before I say something more is the number of one-to-one functions. Now, I need to make a requirement here. I'm going to assume here that the cardinality of A is strictly less than or equal to the cardinality of B for this. Maybe I should put lines under here to separate. This was relations. This is general counting functions. And now I will count one-to-one functions. And you'll see why I need to assume this. Well, it's going to be the same idea as counting functions, multiplication rule, except when you go to assign, well, I'm not going to actually fill in that many. we would assign a value to A1, assign a value to A2, assign a value to A3, all the way out to assign a value to AN, but we don't have all these possibilities. What we need for one-to-one functions is you cannot have two elements of A mapping to the same element in B. That's not one-to-one. Okay, so how do we do that here? Well, thinking about our multiplication rule, we still start off and we pick anything. We pick any of the M elements of B to make f of A1. And in our picture here, that was just my first choice. Okay, this one, fine. But you see the function I have drawn here, it's not one-to-one. When I assign f of A2, I can't choose this one. It already has the element that maps to it. So I only have two other possibilities, or generally I would have m minus 1. So I would have m minus 1 here, because I can choose any element of B for f of A2 except the thing I've already chosen. Okay, now, if I've chosen something for f of A1, chosen something for f of A2, well, now comes f of A3, and I can pick any element of B except the two I've already selected here. So I would have m minus 2 for f of A3 for the same reason, right? If I picked one of these two, I'd have two different elements mapping to the same one, not one-to-one. And this would continue all the way to here. We would have m minus n plus 1 possibilities for the last one. And we've seen this quantity, before in our counting sections. And so the answer here, this was Pmn, which is this, or you could also write this m factorial over m minus n factorial. This is the number of one-to-one functions. And certainly for this quantity to be defined, you need n less than or equal to m. And that's really the only situation I was thinking about here. Okay, so now we have some things we've started counting, and what I want to do now is state the pigeonhole principle, but then we will address this question when, let's see, n is greater than m. So the cardinality of A is greater than the cardinality of B. So let me state the pigeonhole principle, and we will continue on this topic of one-to-one functions. Okay, pigeonhole principle says the following. Pigeonhole principle, and I will say I am going to prove the pigeonhole principle, but not this form of it. I will prove a more general pigeonhole principle later in the video. So for now, I'm just going to state this version and use this version, and then I'll prove this in a more general setting. And okay, so this says if X pigeons occupy Y pigeonholes, and X is bigger than Y, then, now you have to be careful about your conclusion here. It says the following: at least one pigeonhole contains two or more pigeons. Two or more pigeons. Okay, now, this might seem not even like math. I don't know, it's stated in terms of pigeons and pigeonholes. The amazing thing is the pigeonhole principle is very powerful, and sometimes you have to be very creative to use it, but it's a very powerful principle. So we will use the pigeonhole principle in two propositions that have to do with counting functions. Then we'll use it in some other examples. And the first is this. Okay, so for A and B finite sets. Everything I'm doing in this section, finite sets, I would say, let's see, two videos after this, we'll be working with cardinality on infinite sets, things like this, but that's definitely not today. Okay, so for A, B, finite sets, it says if you have a function, or no, I'll say this, if, I'll state it this way, the cardinality of A is bigger than the cardinality of B, then there are no one-to-one functions f from A to B. Okay? Now let's prove this. And we will prove this by contradiction. And it's an if-then. So by contradiction. Let's remind ourselves how we prove an implication by contradiction. If you want to prove P implies Q, you assume P is true and not Q is true. Then you argue until you reach a contradiction. So let's do that here. We assume the cardinality of A is bigger than the cardinality of B. Okay? A, B, and finite sets, we are still working in this case. Cardinality of A bigger than the cardinality of B, that's the if part. And we assume there exists a function from A to B such that f is 1-to-1 with f 1-to-1. Now, we need to argue until we get a contradiction. Well, wonderful. Okay, we use the pigeonhole principle. Whole principle, which says, well, it's stated above, but in order to use this, I'm gonna, what are my pigeons? What are my pigeonholes? Then pigeons must occupy the pigeonhole. So when does a pigeon occupy a pigeonhole? Okay, well, my pigeons, period, my pigeons are the elements of A, capital A. My pigeonholes are the elements of capital B, capital B. And then little a, pigeon little a, occupies pigeonhole little b, little b, well, if and only if f of a equals b, f of a equals b. Okay, now we will unravel, because look, cardinality of A, we have more pigeons than we do pigeonholes. So as cardinality of A is bigger than cardinality of B, ooh, I almost ran out of space there, by the pigeonhole principle, we have, okay, let's see, we have at least one pigeonhole. That's a B in B. So there exists B in B. This is the at least one pigeonhole that contains two or more pigeons. So, and two or more, A1, A2 in A, A1 not equal to A2, and both of these pigeons occupy the pigeonhole with f of A1 equals f of A2, which is B. Now if you look at this, you realize we have our, we have our contradiction. Because we have two different elements of A that map to the same element of B. This says F is not 1 to 1. This contradicts. I'll say this contradicts F being 1 to 1. Okay? So therefore, okay, I was just making sure that I didn't mess up the video when I tripped over my microphone. So therefore, we have proved this. We reached a contradiction, so we have proved if the cardinality of A is bigger than the cardinality of B, there are no one-to-one functions from A to B. Okay, well, let me erase the pigeonhole principle, and then I'm going to use it again, but I'm going to make almost the exact same proposition, but it'll be about onto functions. So you might remember, I believe it was video 2 for functions, where I just did an example. And I had cardinality of A, cardinality of B, and they were small, 2 and 3 or something like this. And I said, well, we will see with the pigeonhole principle that if you have cardinality of A bigger than cardinality of B, there's no one-to-one functions. And similarly, I said something about onto functions. And we're seeing it now, okay? Okay, so what's another proposition? And I will also prove this one using the pigeonhole principle. So I have A and B finite sets. You see, I'm almost copying the same thing, except I'm going to state it for onto. This would be if the cardinality of A is less than cardinality of B, then there are no onto functions F from A to B, okay? So all I've done is just change the statement slightly so that it's the correct statement for onto functions, and now I will erase. And the proof is going to be quite similar. It will be by contradiction. And we will use the pigeonhole principle, except we have to think a little bit because we have a different choice of pigeons, a different choice of pigeonholes, but it's this very similar, I will say, idea. Okay. Okay, so, I'll just leave it for now. We will work in blue. Here we go with the proof. And just like the last one, we will begin by contradiction. Okay, so what this means is we assume cardinality of A less than cardinality of B. And there exists a function from A to B that is onto with F onto. Okay? Again, we use the pigeonhole principle. We use pigeonhole principle. And how do we do it this time? Well, the pigeons have changed. The pigeons are the elements in the image. Elements in the image of F, and the pigeonholes are elements of A. Elements of A. Okay, now how do I assign a pigeon to a pigeonhole? So little b and MF occupies pigeonhole. Little a, if and only if, well, this part looks the same. F of A equals B. Okay? So I have a way to take something in the image and put it in one of the pigeonholes. It's when F of A equals B. Okay? Now, as F is onto, we know a definition of onto is that the image is all of B. So the cardinality of the image would be the cardinality of B, okay, And then this is strictly greater than the cardinality of A. So by the pigeonhole principle, you see we have more pigeons than we have pigeonholes. By the pigeonhole principle, what do we see? Well, we have to be careful again. It says we have at least one pigeon. So there exists an A in A. These are mine? Oh, excuse me. I just said we have to be careful. Pigeonhole principle says there exists at least one pigeonhole. That's this, the pigeonhole. And that pigeonhole has two or more pigeons. The pigeons are elements in the image, B1, B2, and the image. These are different, okay, such that both of these pigeons are in the same pigeonhole or occupy the same pigeonhole. So with f of A equals B1 and f of A equals B2. Now, if you look at this, we have a contradiction. The contradiction is not being onto. The contradiction is that f is not a function because we have f of A. Or we have A and A, I should say, and f maps it to two different things in B, okay? So this contradicts f being a function, and therefore we have reached our contradiction, meaning we have proven the proposition, okay? Again, pigeonhole principle. We had a different choice of pigeons, different choice of pigeonholes, but we're able to prove that the cardinality of A is less than cardinality of B. Then you cannot have any onto functions from A to B. Okay, what I'd like to do now, I have a little space I'm going to erase so I have a fresh board. I would like to make a remark about what we have shown, because we showed it in two propositions. So I'll make a remark about what it is we showed, and then we'll do some more examples of the pigeonhole principle that aren't exactly like this, where it's talking about functions. Okay, so here is my remark. It's a remark about what we have proved, and then we'll restate it. My remark is the following. Well, okay, what's my situation? I have A and B finite sets, right? This is throughout. And we have f from A to B, a function. Here's my remark. So we have proved the following. If the cardinality of A is not equal to the cardinality of B, then f is not a bijection. And let me think, or let me maybe discuss for a moment why in fact we have proved this. Okay, well, let's think about this statement. There's two cases here. If two numbers are not equal, there's only two possibilities. Either you have this, or you have this, right? We have one of these cases, two cases, when we have this not equal. And this one, we proved if the cardinality of A is less than, it's erased, the cardinality of B, f cannot be onto. And if the cardinality of A is bigger than the cardinality of B, f cannot be 1 to 1. Moreover, we know a bijection by definition is a function that's both 1 to 1 and onto. Okay, so here, if the two cardinalities are not equal, one of these is true, one of these will fail, And in either case, F is not a bijection, right? This is what we proved. Now, let's restate this. And this goes back to something that I briefly mentioned after an example in video 2 of functions. And I also said we'd come back to it. So now is the time. So let's restate this exact same proposition. Now I'm going to keep this part the same. A, B, finite sets, and F is a function from A to B. And how am I going to restate this? Well, by restate, what I mean here is contrapositive. We know the contrapositive of a if-then is equivalent to the original statement. And so in fact, we have proved the contrapositive because we proved this. And these two are equivalent. And what does this say? Well, you negate this implies negate this. So the contrapositive says if F from A to B is a bijection, then the cardinality of A equals cardinality of B. Okay? And this is what I mentioned briefly after an example, and it's quite an important thing you can use for finite sets. Maybe I'll put this in parentheses. You can use for counting because, for example, if you can easily count maybe elements of A, and you find a bijection between that and some set B, and set B is hard to count, well, you would know that it's the same thing as the cardinality of A. You have that many elements, for example. But in any case, we will come back to this. In fact, this is going to go into the definition of cardinality for infinite sets. I think 2 videos from now. I haven't recorded it, but that's my plan. 2 videos from now, when we get into cardinality, we will come back to this notion, except we'll be working with infinite sets. Okay, very nice. What I'd like to do now is go back to the pigeonhole principle. And I mentioned, pigeonhole principle is quite powerful, and sometimes you have to be a little bit creative about what are my pigeons, what are my pigeonholes, and how does a pigeon occupy a pigeonhole. But let's do one example of this type, and then I'll state the more general pigeonhole principle and prove that. So let's do one example. Suppose we have, let's say, S is a subset of N, and S is finite. It's a finite subset of N with the cardinality of S greater than or equal to 3. We want to prove there exists, I'll do this in symbols, X, Y, and S distinct, such that X plus Y is even. Now, I will say before I begin this, natural numbers, 1, 2, 3, 4, 5, 6, etc. 0 is not a natural number, okay? Not for me. Move this back. I'll make sure it's still focused. Okay, great. Here we go. Well, we use the pigeonhole principle. We use pigeonhole principle. And how are we going to do this? Okay, well, the elements of S are the pigeons. What are my pigeonholes? This is where perhaps it's a little bit of creativity. My pigeonholes are this even, comma, odd. And then we assign, let's say we assign a pigeon, I'll do it this way, a pigeon to a pigeonhole based on its parity. Oops, pigeonhole based on its parity. Parity means, well, it's a property of integers. You're either even or odd, but not both. We talked about that even in the first week of class. And the parity is the fact of being even or odd. Okay, so you assign the even elements of S to that pigeonhole and the odd elements of S to this pigeonhole. Okay. Well, you notice, so as the cardinality of S is strictly bigger than 2, it's at least 3, so it's bigger than 2 by the pigeonhole principle. What do we have? Well, we have, so there exists, let's say, X, Y, and S. We have 2 pigeons that are distinct, and X, Y are both even, or we have that X, Y are both odd. This is another way to say that we have this one pigeonhole, or at least one, but we have one pigeonhole that contains 2 or more pigeons, right? So it's either this pigeonhole or this pigeonhole that's guaranteed by the pigeonhole principle, and we would have these 2 different things that are in here or 2 different things that are in here, and adding, in either case, X plus Y is even. If you take 2 even numbers, even integers I should say, you add them, even. You take 2 odd integers, you add them, even, okay? Well, we would have had to prove that assertion maybe week 1 of the semester. At this point, we can just state it. Okay, so we have proved this. We found this was pigeonhole principle. Well, what I'd like to do now, and I'd like to use the whole board, so I will start back up here, is I would like to state a generalized pigeonhole principle and prove it. And this will, in fact, we will be proving the pigeonhole principle I already stated with proving this more general one. So the generalized pigeonhole principle, and this one I will prove, which means I have proved, what we already discussed. I started to write pigeonhole pigeon. Okay, sometimes that happens. Well, here's what it says. Let's suppose we have capital N pigeons which occupy, we have N pigeons that occupy, I will say, that occupy K pigeonholes. Okay, so far so good, it reads the same. Well, except instead of X and Y, I have N and K, but in any case, but here's what's different. So then, there is at least one pigeonhole containing the ceiling of N over K pigeons containing, at least. you have to be careful when you state it. I absolutely need to be careful, and in particular, I need to include the word at least here. Okay, so we have containing, oh, I didn't even spell this right. Goodness, containing, at least, the ceiling of capital N over K pigeons. Okay, now let's prove this. And then we will do an example or two of the generalized pigeonhole principle. So proof. Okay, well, this is by contradiction. And, well, I didn't exactly phrase it as an if-then. I could have. But by contradiction, what do we assume? We have N pigeons and K pigeonholes. We have capital N pigeons. And we have K pigeonholes. And what we're trying to assume, let me underline it, there is at least one pigeonhole containing at least this many pigeons. This is what we need to assume is not true, right, in order to get a proof by contradiction. So, okay, at least one pigeonhole containing at least N over K pigeons. What would be the negation of this? Well, it would say that every pigeonhole contains no more than this minus 1 pigeons. This is our assumptions. Okay, what is the total number of pigeons is no more than, what's the maximum number we can have? Well, we have K pigeonholes, and they contain, all of them, no more than the ceiling of N over K minus 1 pigeons each. So the most possible pigeons we can have is this product. But now, what can I say about this? This is strictly less than. Well, this ceiling of N over K, right, where you round up. So I can say that this number, the ceiling of N over K, is strictly less than, oh, don't know what color to use. I have too many options. Well, this number is strictly less than if I just take N over K plus 1. Because I'm rounding up, but I'm never going to jump up a whole integer. So it's strictly less than this. If N over K was some integer 0.1, I'd round up, and this would be plus 0.9. But if N over K was actually an integer, I would just get N over K. So this underlined is always strictly less than this, okay? And then I keep the minus 1. And this is, well, you see, this is just N. So what I have, the total number of pigeons is no more than some number which is strictly less than N. And this contradicts that we have capital N pigeons. And this would be the end of the proof, okay? Okay, let's do an example. And this, what I'm about to say, is true as of 2017. I just Google searched this, but All they gave me is the 2017 numbers, and it's as follows. It's about the population of Boston. The population of Boston is, I have 685,094. And the question is, how many people must share the same first, middle, and last initial? Now, in theory, it could be all 685,094, although I seriously doubt every single person in Boston, let's see, has VMH, which is my first, middle, and last, right? So it's just how many must share the same first, middle, and last initial. Okay, this is going to be a generalized pigeonhole principle example. And let's think about this. So we have 26 letters. And we want to think about the number of first, middle, and last initial like this. This is a list of length 3 or a string of length 3 over this alphabet. Now, again, something I'm also assuming is that everyone has a first, middle, and last of these residents, and that may or may not be the case, but for the purposes of this example, every resident has a first, middle, and last initial. Okay, so we can count these. We have 26 options for the first, 26 options for the second, and 26 options for the third. It's 26 cubed. Okay, so if we think about this generalized pigeonhole principle, my pigeons are Boston residents, and we know how many of them they are right there, 685,094. And my pigeonholes are this list of length 3 are these things, first, comma, middle, comma, last initials, and now we just calculate, right? So clearly the number of pigeons is bigger than the number of pigeonholes. Well, maybe it's not clear because this is something cubed, but it is. But we don't want to just say, well, at least 2 residents have the same first, middle, last pairs. We can use this more generalized version. And so to use this, we would take the ceiling of 685,094 divided by 26 cubed. This is, I have to look because I don't have my calculator. This is 39. So I think in my calculator I got this was 38.9 something or other. Now this is 39, and so this is the answer. 39. Here, 39 residents, at least 39 residents must share the same first, comma, middle, comma, last, oh goodness, out of space, initial, triple, or list of length 3, right? Initials. Now this doesn't tell us in particular which initial pairs out of all of these that is shared, but just there's at least one such that 39 residents share that same first, middle, last combination. One more example. How many people, okay, example, this will be our last. How many people are are needed in a group to guarantee at least 4 were born in the same month. At least 4 were born in the same month. And I don't mean the same month and year, so I will mention perhaps different years. Okay? Well, let's think about the pigeons and the pigeonholes. We have 12 months, okay? In 12 months, these are our pigeonholes. And I will say the N people in the group that we're interested in making, or how many people do we need, and people, these will be our pigeons. And we want to guarantee, so we want, the smallest N such that when you take the ceiling of N over 12, we get 4. And this would be the smallest number of people we could put in a group to guarantee that 4 of them were born in the same month. Well, here you can see how to answer this. It would just be 3 times 12. That won't work because that's 3. When you divide this by 12, you get 3, but you take 1 more. So plus 1, we get 37. So if we have a group with 37 people, we are guaranteed that 4 of them were born in the same month, okay? This is the pigeonhole principle.